We will now briefly review our knowledge of the composition and structure of Earth's interior. Not only will we look at the basics of Earth's internal layering, but also the methodologies involved in how we know, including seismology, gravity, and magnetism. Knowledge of the deep Earth is critical in the understanding of plate tectonics and all related geologic activity, including volcanic eruptions and earthquakes. Indeed, even after more than a century of study, our understanding of the processes that occur in the deep Earth is still evolving. Shown here is a simple model of Earth's interior as we currently understand it. Let's begin by looking at a few areas of study that allow us to understand what is inside our planet, and these include petrology and seismology and some other areas of geophysics, which look at the Earth's gravity field and magnetic field. Seismology is the discipline in geophysics that interprets the structure and composition of the Earth's internal layering using vibrational waves or seismic waves. An earthquake is a seismic event that releases energy that creates a series of vibrational waves that move out in all directions within the planet, away from the source of the seismic event itself. As these waves travel through the various layers within the Earth, they pass through different materials and boundaries. As they do, their velocities and travel paths may change. And so the arrival of these waves is observed and measured at various seismic stations on the surface around the world, and this information is used to interpret both the origin of the earthquake itself and the interior of the Earth through which the earthquake waves have passed. The fields of igneous and metamorphic petrology can tell us quite a bit about the Earth's interior as well. Field studies may include mapping and analysis of rocks that form at depth. Experiments in the lab can also be done that recreate conditions that represent various depths within the Earth. Gravity and magnetic studies can also shed light on the differences in distribution of mass within the Earth. And theoretical modeling can simulate basic differences in the structure and composition of layers within the Earth. The properties of different types of seismic waves are key to our understanding of Earth's layered internal structure. In general, seismic velocities increase with depth. This is because pressure increases with depth, as does rock density, and so both P and S wave velocities will also increase with depth. Seismic waves are typically interrupted when they encounter certain layers, and these interruptions are termed seismic discontinuities. The diagrams here show different models of Earth's interior and the travel paths of seismic waves. In a hypothetical Earth here with no internal structure, seismic waves would trace out smooth arcs within the Earth with no interruptions or discontinuities. Of course, that's not an accurate model for the Earth. This is closer to what we think is going on, and we can see that those arcs are disrupted by the layered internal structure within the Earth. And so this causes some seismic waves to bend as they go through the boundary, and causes other seismic waves to actually bounce or reflect off the boundary. The diagram on the left here shows that P-wave velocities suddenly decrease at this boundary here and then slowly increase again. There is a very small increase in wave velocity again, deeper within the Earth. So the depth of these changes or discontinuities mark the major boundaries by which we draw out the layered internal structure of the Earth. They basically define the core mantle boundary here and actually the boundary between the inner and outer core. S waves, when they encounter this boundary here, stop altogether. S waves don't travel through liquids, and so this tells us not only that there's a boundary there, but what the composition on one side of the boundary is. Must be a liquid of some kind. So this discontinuity represents a boundary between the solid lower mantle and the liquid outer core. Mapping of seismic wave paths show that they may change direction when encountering a boundary between two physically different layers. Both seismic reflection and refraction studies are used to identify these seismic boundaries within the Earth. The figure at left is a simple diagram showing the situation where seismic waves encounter a boundary between two different layers, different density, and the seismic wave bounces off the boundary. This is seismic reflection. And right here is a situation where the seismic wave encounters the boundary and actually passes through the boundary, but its travel path is changed. It's bent, and we call that seismic refraction. Depending on the density of the different layers, the travel path will be bent either towards the boundary like this or away from the boundary deeper into the Earth. These are very simple examples of how we use seismic reflection and refraction to identify different types of boundaries within the Earth. Seismic tomography is a geophysical technique that utilizes seismic velocity data to map out the three-dimensional internal structure of the Earth. So, in essence, lower than average seismic wave velocities usually signify areas of warmer or less dense rock that may exist in volcanic areas or mid-ocean ridges. In contrast, higher than average seismic wave velocities typically represent areas of colder or more dense rock, like you would see in a subduction zone or in the interior of a continent. The figure at left here is a tomographic cross-section of the southwest Pacific Ocean, and here we can see the legend there. So red is slower seismic waves and blue is faster. From what we know, the red areas are slower, representing warmer, less dense rock, and the blue areas are representing colder, more dense rock. Here we can see a colder oceanic plate subducting down into the mantle and a volcanic arc above it, and that's signified by the slower wave velocities there in red. And then we can build a simple geologic model based on this, which shows the subduction of the plate on the right beneath the other oceanic plate, and it builds a volcanic arc, an island arc, and this has all been mapped out by seismic tomography. We can use gravity to explore Earth's interior. Let's first go over a few fundamentals. One is that matter produces a gravity field in all directions. It was Einstein who described gravity in terms of a three-dimensional space where objects with mass bend the fabric of space-time and produce what are called gravity wells. As you can see in this figure, the larger, more massive object produces a distinctive gravity well that's larger than the smaller, less massive objects. Gravity is a force of attraction, and it's dependent mainly on the mass and distance between objects. And so here we have the gravity equation, the gravity, which is a force, the universal gravitational constant g, which we won't talk about today, times the mass of each object and the separation distance between. In essence, larger values for m will give you greater gravity, but also the distance r here. Stronger gravity could be that the objects are very close, so this value of r would be fairly small, and so it would yield stronger gravity. In the opposing scenario, weaker gravity would be produced by less massive objects, and if the distance were greater, the force of gravity will decrease not in a linear way, but as a function of this square of the distance. And so as objects separate from each other, the force of attraction drops off quite rapidly. So how do we use gravity to understand Earth's interior? Well, as a result of the unequal mass distribution within the Earth, Earth's gravity field is not uniform. In fact, there are many places where gravity is higher than average and other places where it's lower than average. And these variations in Earth's gravity are called gravity anomalies. So, positive gravity anomalies are where the gravity field is stronger than average, and these typically result from more mass at depth or higher density material at depth. Negative gravity anomalies are essentially the opposite, where there's weaker gravity due to less mass at depth or lower density material. So mapping the gravity field can help us interpret what is beneath the surface. These different relationships are illustrated in this simple figure. Here we have 3 boxes representing gravimeters. These measure gravity by measuring the stretch in the spring, which is attached to a weight. The more stretch of the spring, the stronger the gravity. The less stretch, the weaker the gravity. The gravimeter on the left shows the most stretch due to the higher gravity caused by some material down here at depth beneath it, which is of higher density. And we interpret that to be a dense metallic ore deposit, maybe. Gravimeter on the right, where there's a lower gravity, a negative anomaly, due to a lower density area at depth. And we interpret this to be a cave. The data is the measurement of gravity, and our interpretation is there's an ore deposit there or a cave. So we can interpret these gravity anomalies to say something about how mass is distributed within the Earth. Here we have a gravity map of Arizona, and it shows many different gravity anomalies, like the large gravity high in the Four Corners area, and the gravity lows across the southern part of the state. These differences in the gravity field are due to the geology at both the surface and well beneath the surface. Let's consider some possible situations where the density contrast between rocks and structures at depth produces a positive gravity anomaly. Many types of metallic ore deposits and some iron and magnesium-rich igneous rocks, known as mafic rocks, have relatively high densities. These buried masses will generate a higher than average gravity signature, a positive gravity anomaly, and that will show up in a gravity survey. And the size and shape of the gravity anomaly can relate to not just the location, but the size, depth, and composition of the buried material. What about geologic situations that result in negative gravity anomalies? There are many types of rock that have relatively low densities, including masses of salt, certain iron and magnesium poor igneous rocks, known as felsic rocks, etc. Certain geologic structures can concentrate low-density material. These include sedimentary-filled basins, volcanic craters, or even impact craters. Cave systems, whether they're filled with air or water, certainly have a lower relative density than their surrounding bedrock. All of these situations will result in a negative gravity anomaly. Again, the size and shape of the gravity anomaly can relate to not only the location, but the size, depth, and composition of the buried material. In this case, this is a salt dome, which is a mass of low-density material that produces a negative gravity anomaly, which can be mapped out. And this is economically very relevant because salt domes, in many cases, produce hydrocarbon traps. These are traps for oil and natural gas, and they are significant in the Gulf Coast region. There are places where buried sedimentary basins exist. We can't see them on the surface, but we know they're down there because they produce a negative anomaly in the gravity field. So these are just a few simple examples of how gravity is used to map out the Earth's interior. Magnetic fields and their properties can be used to describe buried rocks and structures in much the same way as gravity fields. Earth's planetary magnetic field is generated in the core. We will talk about this shortly. On a smaller scale, certain materials have magnetic properties, like magnetite here, and produce anomalies that can be mapped. Positive magnetic anomalies exist where the magnetic field is stronger than average and are due to the presence of magnetic material at depth, whereas negative magnetic anomalies exist where the magnetic field is weaker than average and result from material at depth that is less magnetic. This is a map of Arizona showing the magnetic field, and these positive and negative anomalies largely correlate to the local geology as opposed to deeper in the crust or mantle. Magnetic surveys can be interpreted in much the same way as gravity surveys. The size and shape of the magnetic anomaly can relate not only to the location of the buried feature, but its size, depth, and composition as well. Positive magnetic anomalies are typically produced by metallic ore deposits or iron-rich and magnesium-rich igneous rocks, mafic igneous rocks, which are magnetic to varying degrees. These buried masses will generate higher than average magnetic signatures and show up as positive anomalies in a magnetic survey. Left here is a buried metallic ore deposit and its corresponding positive magnetic anomaly. And right there is a buried gabbro, which is a mafic igneous rock, and its positive anomaly. It's interesting to note that some geologic materials, such as magnetic rock and ore deposits, typically have higher densities as well, and will thus generate both positive magnetic and gravity anomalies. Well, what about negative anomalies? There are many types of rock that display relatively little, if any, magnetism. Again, these are some of the same geologic materials and structures that have lower densities as well, and will thus generate both negative magnetic and gravity anomalies. Examples include masses of salt, certain iron-poor and magnesium-poor igneous rocks, certain geologic structures like buried sedimentary basins, buried volcanic craters, or even impact craters, like this buried sedimentary basin here producing a negative magnetic anomaly. So magnetism isn't useful just for finding buried treasure at the beach. Now let's pull it all together and talk about what we currently know about Earth's interior. The core is made up of two different parts, a solid metallic iron-rich inner core surrounded by a liquid metallic iron-rich outer core. The Earth's mantle is a thick layer of iron and magnesium-rich silicate rock that surrounds the core, and the thin outermost layer is the Earth's crust, composed of both continental and oceanic types. The uppermost mantle is relatively cool and rigid, and combined with the crust is known as the lithosphere. The energy of heat trapped within the Earth has broken the lithosphere into several major plates, roughly a dozen or so major plates plus some minor ones. And these plates are moving around and interacting with each other, and they are moving slowly over a weaker layer called the asthenosphere. And so much of the geology that we experience today is due to the interaction of these lithospheric plates as they move around relative to each other. The lithosphere includes two different types of silicate crust: continental and oceanic. Continental crust has a greater overall thickness than oceanic crust. The thickness of continental crust ranges from 20 to 25 kilometers where it's thin to 70 kilometers or more where it's thicker, and has an average of about 35 kilometers. Its overall density is lower than oceanic crust, and so it's more buoyant, and it gives it higher surface elevations. Oceanic crust has a thickness of about 10 kilometers or less, with an average of about 6 or 7 kilometers. It's thinnest at mid-ocean ridges and might be only a few kilometers thick. Oceanic crust is more dense than continental crust, so it is less buoyant, and that gives it lower overall surface elevations. The mantle is a thick layer of iron and magnesium-rich silicate rock that forms more than 80% of Earth's volume. Direct knowledge of the mantle comes mainly from xenoliths of mantle material trapped in erupted volcanic rocks, like the peridotite nodules in the basalt shown here. Ophiolite sequences are rare occurrences where the uppermost mantle has been scraped off a downgoing subducting tectonic plate and preserved in the overriding plate. Geophysical research and theoretical and laboratory studies allow us to indirectly estimate the structure and composition of the Earth's mantle. The nature of the Earth's core is known only from geophysical studies. Seismic studies have been extremely important in constraining the depths of the various boundary layers. For instance, when an earthquake occurs, seismic waves travel out in all directions into the Earth. Some of those waves are P waves, and they travel through the mantle, But when they encounter the core mantle boundary, their travel paths will change. They will either be reflected off the boundary or refracted and bent through the boundary. This scatters the P waves, creating a band on the far side of the Earth where no P wave arrivals are observed. This band is called the P wave shadow zone, and it is due to the interaction of the P waves with some major boundary layer within the Earth. The same earthquake produces a similar phenomenon with S waves. As the S waves travel through the Earth, they will encounter the core mantle boundary, as the P waves did. But here the S waves are stopped because they cannot travel through liquid. This creates a much larger shadow zone on the far side of the Earth, known as the S wave shadow zone. Both the P wave and S wave shadow zones were interpreted in the early 20th century as evidence for a major boundary within the Earth, and it was interpreted to be the core mantle boundary. Additionally, it was theorized that the outer core was made of a convecting metallic liquid because of the nature of these shadow zones. P waves are also affected as they pass through the inner core, which is solid and iron-rich, and seismic studies later predicted the existence of a solid metallic iron-rich inner core. The dynamo effect is thought to be the source of Earth's magnetic field, and the other planets as well. Dynamo theory describes the process where a rapidly rotating and convecting, electrically conducting fluid layer, Earth's outer core, can generate and maintain a planetary magnetic field. Earth's relatively rapid rotation, once every 24 hours, and its convecting liquid metallic outer core combine to create a magnetic dynamo effect and form Earth's relatively strong magnetic field. Well, that's all for now. Till next time.